Yeah, we're very lucky today to have Andres Diaz-Pinto here. He is a MONAI label expert, developer, and all-around good guy at helping out with many segmentation challenges. And so I'm going to pass it over to him, and thank you for spending the time.
Yeah, can you hear me and see the slides, right?
Looks great, thank you.
Excellent. So thank you, Steve. Thank you, Michael. Yeah, hello everyone. I'm Andres Diaz-Pinto. I'm technical marketing engineer at NVIDIA. I'm going to split this presentation into two parts. So first, what are the new things about MONAI Label, and for those that don't know what is MONAI Label, I'm going to explain a bit what is MONAI Label and also the different use cases. So that will be for the second part. So this is the agenda. What is MONAI Label? Why we should care about using MONAI Label? How to create a MONAI Label app, and the different active learning strategies that we have. So that's the first part. The second part will be radiology use cases, how you can train your own model with the different data sets that are available in public available, and also how we are going to use the AWS infrastructure with MONAI Label, which is amazing. Yeah, so that's the second part. So essentially, for those that don't know what is MONAI Label, is a tool that facilitates the building of AI annotation models, right? So you can easily create AI models, and that means you can train and do inference on single or multi-stage deep learning models, right? It should be very easy for you to create one. That's the idea. And this library also includes active learning strategies to improve model performance. So you can use the ones that are available there based on uncertainty. I'm going to provide more details at the end of this part. The good thing is everything is written in Python. You can, with a simple pip install MONAI Label, you can start playing or training models with MONAI Label, right? We have developed different viewers for the different applications. If you are working with the radiology app, which is CT, MR, or multimodality MR images, you can use the 3D Slicer or OHI viewers. If you're working with histopathological images, you can use the digital slide archive or QPath to annotate those type of images. For endoscopy applications, you have the CBAT viewer, the MONAI Label plugin for that. Great. So that's the bit. So this is the MONAI Label infrastructure that we have implemented. In essence, it's a server client system, but it doesn't mean that you have to use always the server. You can also use the terminal to run a Python script, the main file in MONAI Label. But yeah, those are the two modes. If you're using in the server mode, you have these three main parts. You have the MONAI Label server, right, where we host the different applications, the radiology, pathology, endoscopy, and also the MONAI bundle, which is a specification in MONAI for deep learning models, right? So that's the main part, the MONAI Label server. And you also have the data store, or basically how you manage the studies. So you are working with DICOM images, you can use the DICOM web, standard DICOM web server to communicate with the MONAI Label server. Or if you're working in the local file using a folder, you have a folder with the nifty images or NRD files, you can use the local file archive with a specific way of organizing the data set that I'm going to explain later. But this is one part of the MONAI Label, managing the data store. The other bit are the plugins. So for each type of application, we have, again, the different viewers. We have 3D Slicer or QPath or CBAT for endoscopy, right? Those are the three main parts. Why we should care about using MONAI Label? Essentially, we aim at two personas, right? So there are two type of, say, researchers here. So one is the researcher that want to create new annotation methods, play with a different data set, train a model on a different data set, or fine-tune the available pre-trained models on a new data set. So they also want to create active learning strategies, compare the difference between the active learning strategies, make incremental improvement to the models that we have created and have a as reference in MONAI label, you can do that as well. The other type of persona is the clinician working in a research setting environment. The only thing that he or she cares is about reducing the time money for annotating data sets, right? So they want to, use the preaching model and run inference and see how the model is working and segment the different organs or tissues, right? And for that, again, we have developed different plugins, radiology, pathology, and endoscopy. So I'm going to explain how you can create a MONAI label app. And in this case, I'm going to focus on the radiology app, but this applies, most of the things that I'm going to explain applies to the other type of applications, right? And the first, to set up the context, you have, once you download the MONAI label app, let's say the radiology app, you have this folder structure. You have inside the radiology app, you have the main file. And again, this is it contains the main function where you instantiate the different classes. For the people that don't know, they just basically just know that there is there. You don't need to modify anything there. For the people that are more interested on running MONAI label without starting the server, just as a Python script, the main file is where you refer to, to see the main configuration or how the arguments are read. So the main file is important to run the server or run the MONAI label, sorry, without the server being started. The other part is the lib or lib, where you have the configs files, the infers, and the trainers. The most important one here for the people that wants to play or train new models is the configs file, where you basically define the label names and the indexes to the segments that you want to work on. Okay. I'm going to show you later how it looks like, but it should be very, very easy for you to define that. In the configs file, we also define the network architecture. The good thing about this is that you can use out-of-the-box networks that are implemented already in MONAI. So you can play with SecResNet, you can play with different flavors of units, you can play with the dynamic unit, you can play with networks that are based on transformers. So it should be very easy for you to use that in MONAI label, right? We have provided several as by default, but you can change that very easily in the config file. Yeah, so that's the context, that the structure of the radiology app, or any MONAI label app. So the first thing, if you want to create a MONAI label app, is ask the question, what is the data set that I'm working on? So am I using CT? Am I using MR? Am I using histopathological images? Am I using which type of images? How many modalities, right? So that's important to ask. So that basically allows us to define, okay, I'm using the radiology app because I'm using CT images or MR images, radiology. I'm using 2D images or videos for endoscopy videos. So I'm using the CVAT. So that basically tells you which type of app you want to use here. Okay. Okay, so that's the next thing. The second thing, and probably the most important one, is how you organize the data set. And let's take this example. So I have my data set, which in this case is a whole body CT segmentation data set, specifically the total segmentated data set. And you see, it follows this organization. The one on the left, you have on this data set, you have one folder per case or per patient, right? The 0000. In that folder, you have the CT image, and within that folder, you have the segmentations, which is 104 segmentations. Each segmentation has one file, right? So this is the original for the organization of the total segmentated data set. If we want to use MONAI label to train the model on that data set, we need to organize it in this way, the figure on the right. So you see, MONAI label is you can call it whatever you want. I call it MONAI label folder, right? Inside that folder, I put all the CT images with the use case name or any name that you want to put there, right? So you put the CT images inside that folder. You also put labels and then final. And in the final, it should contain the images, sorry, the annotations per each image into a single file. So you need to merge the annotations into a single file. It's very easy. We have the script, the total segmentated repository. There's also a script that you can merge the segmentations into a single file and use MONAI label for that, right? So this is basically the folder organization that you have to train the model in MONAI label, right? So this is an example from the original organization into MONAI Label organization. And this is the script that you can use to combine the masks and use the MONAI Label to train the model on that. Okay. And the last bit is say, I want to use the total segmentator data set, but I don't want to train it on 104 segments. I want to train it on say, 20 segments, which is or 20 organs that are the most interesting, or 4 or 2 or 1, right? The number that you want. So how I define that? Basically, I go into the configs file, right? The segmentation.py file, and define the label names that I want to work on. I want to train my model on, and specify the indexes, the numbers associated to each segment. And that's provided in the data set, in the total segmentator data set. So you see it's not from 1 to 24. Each segment has a different index, right? 1, 2, 3, 4, 5, 6, 7, 14, 16, and this from 17 goes to 42, esophagus, right? That's the way they put the number, but you can change that in the data set. You can also do that. It's quite flexible, okay? But if you don't want to change that, you just define the label names and numbering from the original data set. And in that's the way basically you create a new MONAI Label application, and you're ready basically to train a model in MONAI Label, right? Using that data set. Once you train the model, you can use the active learning strategies to improve the model, right? And how does it work? You basically create one model, make the model to sort the data set, the unlabeled data set. So every time that the user or the expert wants to annotate a new or modify the predictions from the model will send the most difficult one, right? The expert annotate that or correct the prediction from the model, and then retrain the model or fine-tune the model. In that way, we will get the model better and better working on the data set or the labels that we want to work on. And with that, I'll finish the first part of what is MONAI Label and the things that you could do to train your own model. And the second part, I'm going to show the different radiology use cases and how, in more detail, how you can train models on different data sets or fine-tune the model on a different data set than the ones that we provide. Thank you, Michael, or Steve.
That's great. So there's a couple questions on Discord. I don't know if people want to ask high-level questions now, Andres, or do you want to wait until the Q&A session at the end?
We still have a couple of minutes, if that's okay. I mean, I can answer the question.
Yeah, if somebody wants to put a question either in Discord or in the chat here, we'll just take a minute to see if there are any high-level questions before we dig into the next topic. Or unmute yourself if that's an option. Well, maybe in the interest of time, we'll keep moving and then people can ask questions later. Let me take over screen share for a second here. The next thing we wanted to do, just to give you guys a heads up, now that you've got a kind of a refresher or either a fresh look or a refresher on MONAI Label, the things we wanted to do, we'll give you a minute to hear about how you can make use of this conveniently on cloud computing resources, and then more about AWS implementation and what's going to be coming up during the hands-on session. And then we'll hear from 3 clinical perspectives on the use of MONAI Label and how to put what Andres just presented into practice, and then we'll do a deeper dive and hands-on. So the first thing, maybe Rudolf, you want to say a few words about this project. I put up the link here about how to run on an AWS cloud server, and just quickly on your experiences.
Yes, can you see my screen? Hello, this is Rudolf Bumm from Switzerland, Kur, Switzerland, and I will shortly comment on setting up the EC2 instance on HWS, which we've done during the last weeks, and it's working nicely. So if you go to the project page of the project week, then you can find here how to set up and run 3D Slicer on HWS cloud server. and all necessary steps for doing so are documented in a separate document. And you have to consider some things, and you have to deploy a CloudFormation template, which is quite easy. And then you have to wait for 20 minutes, and after that you will get your own EC2 Windows instance, which can be used on and off and can be upgraded and downgraded. It's not the purpose of for using it at this workshop here, but it will be helpful if you use 3D Slicer in different clinical surroundings or in while you travel. And I can just show you briefly that it really works. Usually I go to this nice desktop visualization client, and I just log into this server, and I have to and then make a password, and then I'm on this machine, which is a strong computer with A10G NVIDIA GPU and 24 gigabytes of dedicated video memory, and you can run 3D Slicer here without a noticeable lag, and it's working excellent. I've used it for hours for analyzing bigger data sets. I show some results later. So if you are interested, just go to this page where it's all written down step by step how you can create such an EC2 instance. I'll be at the project week in Las Palmas, and I can show you also around in the system, and maybe we can set one up together. Thank you.
Excellent. Excellent. Thank you. Now, I think either Ching or Alex, who wanted to pick up next?
It will be both of us. Thanks, Steve. Ching, go ahead and share our slides.
Yep.
Thanks. So thanks for the invitation, Steve, and also a warm welcome from our side. My name is Alex Lehman, and I'm the BD so Business Development Manager for Medical Imaging Innovation here at AWS, and I'm here together with Ching Liu, Senior Solutions Architect with focus on healthcare. In this really short section, we would like to briefly discuss 3 things with you, because we will run today's labs on AWS infrastructure. And therefore, we would briefly talk about the benefits of running MONAI Label on AWS. And then I can actually also show you different kind of options, how we can support you and your organizations to get started using MONAI as a whole, using the AWS cloud, similar like how we had the pleasure to support Rudolf. And last but not least, Ching will also give you a short introduction regarding today's lab architecture, which will help you to navigate the labs later much easier. When it comes to the benefits of running MONAI Label on AWS, you see that we try to cluster it around 5 major pillars. So the first benefit is that we as a cloud provider, we provide you a wide range of different kind of GPU instances, which you really can tailor for the underlying annotation workloads and your specific requirements. Again, similar like Rudolf did it. When it comes to security and access controls, we give you a bunch of tools to secure and encrypt your data in transit or at rest when you transfer your medical imaging data. And we have plenty of options so that you can actually implement fine granular access controls so that only authorized systems, applications, and users actually access your annotation applications and your data. The next 2 points, scalability, high performance, plus cost optimizations, are actually highly related, because the cloud gives you the option to automatically scale your infrastructure up and down based on the underlying traffic, which automatically has an impact on costs, especially when you, for instance, run so-called on-demand instances, when the cost goes down, when traffic goes down. And last but not least, when you run MONAI Label on AWS, you of course also benefit from a really tight integration from the further downstream MONAI components of the MONAI framework running on AWS, and from other medical imaging specific AWS services we offer, like for instance, HealthLake imaging for storing and managing DICOM data at scale and at very low costs in the cloud. All of the benefits you see here for MONAI Label, of course, also exist for different kind of MONAI components. And if we now have a look at MONAI Core in particular, I'm not going to any of the details on that slide, but like to highlight just a few things. So what you see here in front of you, this is not MONAI Label related. It's actually machine learning training pipeline based on MONAI Core, which we migrated to Amazon SageMaker, which is our fully managed machine learning service, where we target researchers and data scientists. So it's more managed infrastructure for researchers and data scientists than clinicians. And in order to mimic a real world cutting edge medical imaging project, we inflated the well-known BRADS dataset to terabyte size, and then benchmark different kind of infrastructure configuration against it. And I'd just like you to focus on the table in the upper right corner, where you see that we were able, using different kind of SageMaker components of our machine learning stack, to bring down the training time from originally 90 hours, just using a simple instance, to just 4 hours, really benefiting from different kind of cloud components in combination with MONAI Core. When we, and you can go to the next slide, Ching. When we now talk about how to help you, how you can get started with MONAI in general on AWS, what we provide for you and your organizations really tailored workshops, which can be half a day or full day workshops where we come in, can also be virtual, to run so-called machine learning immersion days. So based on MONAI Label, MONAI Core for medical imaging. We also provide a bunch of tutorials and also conference-wide workshops. So this is like for a lot of organizations, for instance, as part of GTC or RSNA. Last year at RSNA in Chicago, we hosted the MONAI Core and SageMaker workshop. This year, similar to what Michael highlighted, I also like to highlight that we will run a 3-hour MONAI on AWS workshop as part of GTC in the week of March 20. So the final date is not yet decided. In this 3-hour workshop, you will actually touch all of the MONAI components, starting with MONAI Label, MONAI Core, and the 2 MONAI Deploy components on AWS end-to-end using a single example, so single data set. We also, on a constant basis, publish AWS blog posts and solutions. So if you just take a look what we did in the last roughly 1 year, we published 5 blog posts based on MONAI, together with 2 AWS solutions and 1 reproducible workshop. If you are interested to start a POC or you need in-depth support, for instance, to migrate an annotation pipeline or training pipeline workload or a machine learning pipeline to the cloud, similar like what Rudolf did, we are also happy to help either ourselves or together with partners. So never hesitate to reach out, and in the wrap-up email Steve will send out after the workshop, we will also include a list of publicly available MONAI resources which help you to get started. With this, I'd like to hand over to Ching, who will talk a little bit about the specific infrastructure setup we provide today.
Great, thank you, Alex. So in the next few minutes, I'd like to give a quick overview of the workshop setup and then how to access the workshop environment. So first, let's take a look at the AWS service that has been used to support this workshop. It's called Amazon AppStream 2.0. So this is an AWS service that kind of enable you to remote log into the server running the cloud. And from the end user perspective, no software is required to be installed on the end user's computer. All you need is a good and stable internet connection and a modern browser such as Firefox, Safari, or Chrome. And then you are able to use your browser, connect to the AppStream service, and then start using the virtual desktop environment. In terms of the applications available in this virtual desktop environment and data, they remain on AWS. Only encrypted pixels are streamed to your browser. So it's a secure environment as well. In AppStream, we offer a variety of server sizing based on your workload. So these different server types offer different CPU and memory configuration. So you would pick the server size that is based on your workload. So for today's workshop, since we are using MONAI Label and 3D Slicer, we need instance or server with GPU resource. So that's why we're using one of the graphics server types here. So specifically, we're using graphics G4DN server, which has a NVIDIA T4 GPU. So in terms of the server setup, we would like to provide an environment that is ready to use. So you don't need to worry about setting up the MONAI Label server and 3D Slicer. So what we have done here is, we have a pre-built Linux server with 3D Slicer and the MONAI Label environment already set up. And then we use this Linux server as our golden image or a blueprint. Then we deploy many AppStream instances based on this golden image. So every user, when you log into AppStream, you will get the same server configuration and 3D Slicer and MONAI Label environment already set up and ready to go. In terms of the server sizing, we are using the Stream Graphics G4D and 4X large instance type, which has 16 virtual CPUs, 64 gigabyte of memory, and with an NVIDIA T4 GPU with 16 GB of GPU memory. So every user, when you log in, you will get a dedicated server. It's not shared with others. Also, to improve the user experience, we have utilized AWS data centers across the globe. So we have data centers in US, Europe, and Asia Pacific to support this workshop. So based on the information you provided in the registration form, we will assign you to an AppStream from a data center that is close to you. So now let's talk about the workshop access. So in the next half an hour or so, please look out for an email that looks like this. So this email is sent by the AppStream service to invite you to log in. It contains the login link. The login name would be the email address you provided in the registration form, and also a temporary password. So just click on the login link, and this will take you to the login page where you put in your email address and temporary password. If you're logging for the first time, it will ask you to create a new password. But after that, you should be able to see this screen where we have 3D Slicer available as an application for you to launch, as well as 3 MONAI Label server scripts to start up MONAI Label server with different AI models and data sets. So if you are having issue logging to AppStream, or if you haven't received the email within the next 30 minutes, please reach out to us. I think we are via Discord, and we are happy to take a look at the issue for you. And finally, just want to mention that we have a publicly available workshop called AI Assisted Medical Image Annotations. So what we're doing here today is like a simplified version of this workshop. So if you like to set up this environment in your own AWS account, feel free to follow this QR code and this URL. It contains step-by-step guide to help you set up this environment in your AWS account. So with that, I'll hand over back to Steve.
Thank you, Cheng. This is great. So yeah, just everybody keep an eye out for that email. And in the second part part of the course towards the end, we'll have a lot of time for hands-on. Everybody will have a server. I think all the email addresses now are correct. There were a couple typos, but that list from the registration page will be used. So contact us if you end up not getting an email. So now we're going to shift gears because all this infrastructure probably in the last year has evolved quite rapidly. And one of the things that it's enabled is the ability to apply it to a lot of clinical cases. And we thought it would be good to spend time with some of the experts who have been applying this kind of analysis to real clinical problems. And we wanted to start with Rudolf and let him talk about his work in lung. You've seen a little bit of his environment already, and then we'll switch to stroke and then spine and cancer in the spine. So go ahead, Rudolf. Thank you.
Thanks, Steve. I will shortly show some of our results that we've generated during the last month. This is all done with 3D slicer extension called Lung CT Analyzer, which is a spin-off of the COVID-19 pandemic. And Andres and I have done a use case during the last project week, which you see here, where we have set up MONAI Label on a PC with moderate and high-end NVIDIA GPU and made it analyze the lungs and the airways. That worked quite well. But in the meantime, shortly after the workshop, we were able to integrate new AI tools into Lung CT Analyzer. It's not only MONAI Label, it's also Total Segmentator and Lung Mask. And we can now segment lungs, lobes, and airways in a very good quality without any user interaction. And this can be unattended as a batch operation and takes about 150 seconds per case. It can be done in DICOM folders, NRDD files, or with Nifty files. And it has been tested on these HWS EC2 instances already. So this is the kind of quality that you can get now from an AI lung and airway segmentation, which is astonishing. So for surgical planning, we use this kind of setup and we do some manual segmentation of the vessels and the tumor, and we can orientate ourselves in 3D space, which is very helpful. Finally, I would like to comment on working with lung CT databases, because now is the time where we can really switch to bigger databases. And, you know, there's IDC, there's a total segmentator training data set. MONAI Label has his own data set with 8 gigabytes. But I want to comment today on this great data set of Paolo Safino. I saw Paulus in the audience today, and he has 81 COVID patients with 93 CTs, and it's all published and publicly available. And we ran our software over these CTs, and it's quite easy. The analysis, emphysema is green, ventilated is blue, infiltrated orange. You see it all here. And on a strong desktop PC, segmentation and analysis takes around 151 seconds per case. So you can do all these 80 cases in around 3 hours in a row without touching the computer. And now you see some results here. Paolo has asked an expert radiologist to score the images from 0 to 5. This radiologist had over 20 years of experience. And here is the computer analysis affected percentage on the y-axis. And you see that there's a nice correlation, and you can also quantify the correlation, which is 0.85 computer versus human analysis in these 80 patients. You can also, of course, have a look at the lobes. Are some lobes more affected than the others? And you see, as expected, that the lower lobes have higher values here than the middle and the upper lobes. This becomes even more important when you only take data from patients with a radiology score over 2. Then you see the differences become even more marked. And last but not least, the computer can already predict the need to take the patient to the intensive care unit. This is highly significant, the difference between no intensive care and yes intensive care in this data set. So finally, this is the only small script I'd like to show you, and this is the only thing that is necessary to add, for example, MONAI label in your own Python script and to perform inference on your data set. You connect with the MONAI label server, then you do the inference, and that's really all you have to do. Of course, you have to train the model before, but you can then use these kind of artificial intelligence in your own 3D slicer modules. So in summary, I find it still quite easy to set up and call MONAI label from your Python scripts, and it's now ready for unattended batch operation. As I showed you, you don't have to do anything manually anymore. Human versus computer analysis already shows a good correlation. And when you start MONAI label from scratch, it's, from my opinion, the best to use your pre-existing segmentation tool and submit labels to the MONAI label database and then train. And you really can expect more coming and concerning organ and structure support, level of detail, and speed. It will all be much faster in the next half year. Thank you very much.
Thank you, Rudolf. That is really, for people who have ever worked in this field, a remarkable progress in the last year. So thank you. I want to switch gears now and show you some pre-recorded data from a presentation from a colleague in Sydney in New South Wales, Australia. Given the time zone, we decided it was better to pre-record these and let you hear from Dr. Butcher himself. So I'm going to go ahead and play this, and we'll catch up with Ron at the end of these videos.
Hi, my name is Ken Butcher. I'm the stroke.
You able to hear that well, Andres?
Sydney, Australia.
Just a bit.
So, does the sound come through?
Yeah, the sound comes, but it's really
okay.
Can we increase it?
My label and how we've used it to address a very specific problem in stroke assessment. I don't have time to make you all stroke experts, but I am going to have to introduce you to stroke imaging. These are CT scans that I'm showing you right here. These are 2 different patients who suffered one particular type of stroke. This is a hemorrhagic stroke or intracerebral hemorrhage. The blood appears white or bright on CT scan. And you can see that this patient's had a relatively small hemorrhage and this patient's had a very large hemorrhage. And you probably would guess that this patient did better than this one. In fact, this patient died well. And this top patient actually survived and recovered and returned to their pre-stroke life. And we know from very careful studies that were actually completed while I was in medical school, that if you measure the hematoma volume using something called planimetric measurements, you can predict mortality, and there are different thresholds for mortality and good outcome. Now, planimetric measurement is what clinicians call this. Most of you in the audience probably call this image segmentation. They're really the same thing. It's outlining a portion of an image and then calculating the volume based on that three-dimensional outline. Now, for most of my career, in fact, all of my career, that's really been a research tool. The planimetric measurements are time-consuming, and they're part of my research life, but they're not part of my clinical life. When I look after these patients clinically, I get reports from radiologists that look like this, where I get a qualitative assessment. These were both described as large hematomas, even though this one is actually twice the volume of this one. And it isn't just radiologists that do that. We as stroke specialists and neurologists do the same thing because we don't have time to do those measurements. I have spent many hundreds or thousands of hours outlining these lesions through my career as part of my research efforts, and I've trained countless students and trainees to do the same thing, but we simply can't keep up with the clinical workload. And it's been a dream of mine to have those clinical tools and my research tools come together. I've searched in vain until really just a few months ago when I stumbled across, ironically enough, a MONAI Project Week presentation, and I know that Dr. Bumm is there with you today or presenting as well. And I watched his presentation on segmentation of lungs. And I also watched all of the MONAI Label videos presented by Andres. And following that, I actually reached out to Andres, who was very generous with his time and helped me set up my own solution. And the solution that I installed, unlike Dr. Bumm, I didn't install anything locally because I don't have a gaming computer, but I do have an AWS account, and I basically replicated the solution that was described in that last Project Week solution. The only exception is I did play around with the AppStream connection, but I actually didn't find I really needed it, and I use my local instances of 3D Slicer, which I have on my Mac here at home, I have on my PC in my office, I have on my laptop, and I also have a Linux computer here at home, and they all have Slicer, and I'm able to connect to my EC2 instance without any difficulty, and essentially replicated the solution. This is the infrastructure that I utilized on AWS. I requested a G4 extra large EC2 instance, which took a few days to implement because that's not an everyday request, but I did obviously need the GPU processing power to train the models on MONAI Label in a timely manner. And then I essentially followed the instructions provided by Andres in his videos. I installed a Conda environment, used the pip install package to deploy MONAI Label. I had to modify the deep edit Python configuration file. Essentially, I took the spleen model and then changed the labels, as you can see here, to reflect what I was interested in, which was not anatomy, but pathology in the brain. And then I started the server on the local host and accessed it through, as I said, my local Slicer applications. And now I'll just show you a live, quote unquote, demo of one of the models that I've implemented for CT. Okay, here we are. This is my local Slicer application, which, as you can see, is connected to the MONAI Label server running on my EC2 instance on the local host. I have enabled developer mode, so I can increase the number of epochs from the default 50 Though the particular model that I'm going to show you today has actually been trained only on 100 epochs. That being said, I did have 72 cases, and we did the usual 80-20 training validation split. You can see I've entered a number of cases. I've uploaded them simply to show you how well the inference model works today. These are the labels I described to you earlier that I edited the deep edit module with. You can see that most of these labels are actually not going to be relevant today. They are related to other types of stroke. And this is what I call future proofing. The concept is that the MONAI label server app will be labeling all scans as they are sent to it from our PAC system, and it will be identifying all lesions, not just the hemorrhagic lesions that I'm showing you today. But I haven't actually begun training most of these different lesions yet at this point, as that's a much more complex task. So I'm actually going to start with something rather mundane. This is a patient without a hemorrhage. This is a patient who actually had an ischemic stroke, and you can't see anything on the CT scan. I'm going to run the inference model, and you can see that it didn't label anything, which may be a boring place to start, but that's really important when you're, again, trying to run something as part of a clinical workflow or a pipeline, because you do not want it calling out false positives. That will drive clinicians insane. So let's move on to some cases with some actual hemorrhages. We'll just change the presets here too. So here's a fairly large intracerebral hemorrhage, and let's run the inference model. See if we can go as fast as Dr. Blum's. I think we're pretty close. And that green is the intracerebral hemorrhage or hematoma volume, and that is pretty good. You can see that in 3 dimensions. Now, the yellow, it's called ventricular hemorrhage. That's actually a very difficult hemorrhage to localize. It's getting close. There is some intraventricular blood here and here, and it's picked that up. It hasn't got all of it, but it's getting there. You can see that there's still work to be done. There's still some hematoma that hasn't been included out here, and I'm pretty particular, around the edges. It probably has gone over just ever so slightly. It gets a little blocky. Looks like something out of Minecraft when I run the inference model, whereas when I do this manually, it's a very smooth border. And that may simply be a representation of the ROI. I need to discuss that with Andres. But regardless, the volumes are going to be very, very close to what we would calculate manually. And when I've shown my colleagues, they were very, very impressed. And this is very early days. And as you can see, we can get the volume from the region of interest. Now that we have that there, and you can see that it's calculated that as a 73 mil intracerebral hemorrhage, which is, I can tell you, going to be very, very accurate. It's going to be within a few mils of what we would call the gold standard, which is basically manual labeling. Let's just take a look at a couple of others. Take too much of your time here, but we can have a look. Here's a fairly complex case. We'll just have a look. You can see this hemorrhage is very lobulated, but it's picked up, again, it's picked up most of the hemorrhage. That's actually a specific type of hemorrhage I haven't trained it on yet. That's subarachnoid hemorrhage, but I'm pleased that it didn't call it part of the hematoma. And we have to accept that this is a much more difficult task we're asking the model to do here by labeling blood not only identifying blood in the brain, but also identifying the different compartments. So I have to say I'm pleased with the progress to date. I'm optimistic that we will be able to optimize the model in the near future. And I'll just show you one last one if you're not convinced this works well. And that's excellent. If my student brought me that, I would have a hard time being overly critical. I probably would, just because I am, but I wouldn't be displeased at all. Okay, just a few words on where we're taking this project next. Job one, of course, is to continue to refine our model. We need to train it on the other stroke pathologies. We obviously need several hundred more patients, and we want to improve our diagnostic accuracy, but I'm very optimistic that we'll be able to do that over the next few months. The other thing we need to do is move out of what I call the data silo. What I didn't tell you is everything I've shown you today is done offline. So this is a local research database that I have accumulated over the years doing trials in patients who give consent. We take their data out of the healthcare system, we anonymize it, and then we upload it as nifty files in order to do things like I've shown you today. And that's traditionally how research is done, local on-prem data duplication, which has inherent risk for security, etc. And it's just inefficient. That's also how clinical data is collected. Again, very inefficient outside the normal clinical workflow. We have a separate research workflow system. And I've recognized for some time that we need to get out of these data silos if we're ever going to make these research tools part of the clinical workflow and useful to clinicians who are not doing research. What I've shown you today is actually not a lot different than many studies that are published and out there. I get one of these to review about every 2 weeks. They're very similar PyTorch CNN models done on very small numbers of patients, showing the success of segmentation. And they're going to go nowhere. And the reason they're going to go nowhere is they are just projects that I've shown you, similar to what I've shown you today. They're offline, anonymized data, and they're not integrated into clinical workspaces. We recently participated in an AWS data lab where we actually implemented the MONAI label solution inside our health network infrastructure. In New South Wales, we're fortunate enough that our statewide enterprise image repositories are a long-term repository, and also all of our acute imaging for the telestroke program, which I'll share with you, is actually hosted on AWS infrastructure. It's an AWS eHealth Enterprise Cloud. But what that means is we can implement AWS tools, including EC2 instances, SageMaker, and things like MONAI Label inside the health ecosystem, which for a stroke researcher is a little bit like being given the keys to the kingdom. It's really exciting to be part of a project like this, and I'm happy to say that the data lab was a success. We were able to implement MONAI Label in the eHealth cloud. We did identify problems, and one of the big problems is we need to, and I think Andres might be talking about this today, we need to improve the way MONAI Label handles DICOM images, or we need to improve the way DICOM images are sent to MONAI Label, one or the other. But unlike the research world, which is dealing with the nifty standard, in the clinical world, all images are stored using the DICOM standard, and that's what we need to deal with if this is going to be a clinically useful tool. But our concept is that the images will go from our statewide repository to the server. They'll be labeled and sent back to our enterprise viewer, for imaging along with the label, with the volume. We can also send that quantitative data to SageMaker, where we're also developing a predictive model, machine learning based model, using the quantitative data, but also the labeled clinical data for predicting outcome and response to therapy. And the potential is just massive. There are problems, obviously, that we need to occur, but we're very committed to this. This is a map of the telestroke network that we have in New South Wales. So you can see we provide services to patients in 23 different communities. We've provided consultations over the last 2 years to over 3,000 patients. All of that clinical data and imaging data comes to us, and it's all in that AWS eHealth Cloud. And that means if we do successfully implement this, we will, I think, certainly for the first time in my career, truly have that active learning framework implemented, where we can continually train and refine our predictive models and use these things clinically. And I will stop there. I hope I didn't take too much time, but thank you very much for your attention. And I'm sorry I couldn't be there with you today.
Okay, well, that really was impressive to me, because I just met Dr. Butcher just a couple of weeks ago, and his work, I think, is a great exemplar of what somebody can do with the right motivation and just a little bit of support from the community, probably a lot from Andres, but he figured out a lot of things on his own too, obviously. The third clinical use case we want to present, Ron Alkalay. Ron, are you ready to go? Is related to cancer in the spine. And I know there's a very interesting set of issues still under investigation. Ron, are you ready to go?
So I can share my screen with you.
There you are.
Yeah, okay. So this presentation is a little bit different, as I'm not an imaging person, but it's really it's the wish list or some of the problems we're facing and some of the solution we're hoping to get to. So my work is really trying to look at prediction of fracture risk in patients with metastatic spine disease, which is a huge clinical problem. So cancer, as you know, is very prevalent both in men and women. And these are just a large portion of cancers. When cancer essentially metastasizes to the spine, it's metastasis in most cases at advanced stages. Bone metastases usually cause severe pain. They are associated with pathologic vertebral fracture. In up to 50% of these patients, you have neurological symptoms, and the image on the right shows you a large, retropulsion into the canal, and the color screen shows you the effect of that anything underneath that retropulsion is pretty much damaged. So the paralysis and is very common in this patient, and that's a huge societal and cost for both the patient and the resources. And essentially, if the patient does have this kind of fracture, his survival and morbidity goes way down. Okay, the problem is that current prediction methods are really, based on classification, like many other systems. This is called the SINS protocol, which is the most prevalent one. It's really used for characterizing patient. However, there's very little agreement between different patients for different domains. More so, there's a very poor inter-observer agreement regarding what actually happens in the vertebra. There is essentially nearly no agreement about what is the implication regarding bone strength, which ultimately predicts fracture. And not only that, but SINS, based on our work, is really not predictive of fracture risk. So we need to come with something else. So clinicians really rely on past experience of selecting patients with surgery. There is prognostic protocols offer currently poor prediction, quality of clinical decision vary greatly based on experience and center. And there are also substantial barriers to precision intervention. And ultimately, trying to figure out whether to select patient for a treatment really follows the type 1, type 2. Either you essentially treated the patient when he did not need treatment, you cause a lot of morbidity, or alternatively, you deny the patient treatment when he needed one, and also cause a lot of morbidity for the patient. So if you think about healthcare, we really need a patient-specific precision medicine paradigm to support clinical decision, either to offer withheld surgical intervention and also predict the patient risk. So that's the overall goal why we're interested in it. So we currently run a study, and it is a clinic observation study in a patient treated for radiotherapy. And we get CT and MR at baseline at radiotherapy. And then the other unique thing in this study, we also get longitudinal CTs for those patients. So we get them at 3, 6, and 12 months post radiation therapy. And the aim would be to see, can we predict fracture either post baseline at 6 months or at 3 month intervals, to try and figure out, whether we should or not propose a treatment for the patient. And our hypothesis, obviously, that we can predict the fracture risk based on imaging. Okay, so this is just a brief indication of where we are. We hope to enroll about 320 patients. We currently have 164 patients with a wide variety of cancers. 25 of our patients already fractured. Actually, it's 30 patients by now, and we have about 45 fractures in this study. So if we look at the fracture, even though the biology is very complex, ultimately it's a mechanical event. And the reason for the fracture is when the vertebra can no longer carry functional load. And there's a very simple concept called fracture risk. If that ratio of load to vertebral strength is above 1, fracture will probably occur. If the ratio is less, which means the vertebra is stronger than the load applied to it, fracture probably will not occur. That's a very simple concept, but it works from a generic perspective. And part of it is based on work looking at, activity versus spinning loading, and shows that for different activities, you get very different loading. And just to orientate you, if let's say you bend forward, your loading actually is predominantly at the lower spine. If you hold weight in your hand, loading is predominantly at the thoracic spine. So activity changes the loading each vertebra sees, and that will change the load to strength ratio. And the other thing which we found out, that actually that load to strength ratio is associated with the pattern of fractures. So knowing what loading or what the muscles do in the vertebra is very important. So ultimately, the way we look at things, we take the CT, we then create musculoskeletal models for those, we then simulate the daily task, and from that we get vertebral loading. On the other hand, we take the CT, we either use a rigidity measures, looking at bone strength and cross-sectional area to compute the strength of vertebra. We use finite element analysis, and from that we get vertebral strength. Dividing that ratio gives us factor of safety. Okay, both of these activities actually require segmentation as the first part of all that. So currently we have, for our study, we have about 140 spine manually annotated. Segmentation is really challenging, because in cancer vertebra, unlike elderly vertebra, there's a very limited contrast between the bone and the soft tissue. The bone is very rarefied. Partial wall, essentially, because the image cannot also separate the anatomical structure, you get a lot of connection between structures, and there's a lot of work to try and separate them. And ultimately, to try and manually segment a spine and doing a good job, it can take up to 14 hours per spine. Currently, we're hoping to have 329 patients at 3-6. So we're talking about 1,200 spines just for this study, indicating 1,200 to 1,400 man hours. So you can have an army of students, but that's probably not the solution. And also, we would like to train, our future plans are looking at 6,000 patients from the Framingham Heart and retrospective. So really the challenge is develop a fast method that allows to do less than 5 minutes per spine. That's the challenge regarding this one. Looking at muscles, for instance, we have 140 patients, and that's really one of the unique aspects of our study, which has been annotated for spine muscles. So we do for every level. So we have essentially 16 levels times 16 muscles times 12 levels, 140 patients. You can understand it takes a long, long time. And muscles are really important, and they're becoming more and more important clinically, how they affect, because it's one of the biggest tissue in your body, and in cancer patients, there's a lot of changes. So we need to understand how muscle affect our work. Okay, so part of what the work we've done, we just got some a supplement from the NIH, and our co-investigator is Sandy Wales, Steve is a co-investigation, Nazim, and David Hackney. And the idea is to take our data set and curate it for the training of machine learning. And essentially, we take all the 140 patients, the CT data, and we then look, provide spinal column data, muscle segmentation, annotation. That data will become public data for people to be able to train on. And some of the work already done, we've used MONAI and total segmentation. So Andres has been incredibly useful and helpful over the years, despite my total lack of knowledge of anything computers. So, this looks extremely promising. And ultimately, take the full spine segmentation is currently taking us about 3 minutes. So we're getting there. And we still have some work to do because the way most model trained is on data which is lower resolution than our data. And our sample sets are very, very big, requiring GPUs with at least 48 gigabytes of memory just to run that kind of segmentation. And one of the nice things is we can then start to look at longitudinal studies. So this actually shows you a 0 and a 3-month segmentation. And actually, when you look at the vertebra, some of the changes are due to actual shape changes due to cancer. So that's something nice that we can look at. And very exciting is we can start to look at development of lesions. So the lesion on the left, it is radiation planning, 3 months post-RT and 6 months post-RT. And not only does the lesion grow, but the characteristics of that lesion is changing remarkably. So, part of it, I suppose, is because of the different medium of the CT scan we've done. But I think that is a great target to start to see how does the, spatial characteristic of that lesion affect the fracture of that lesion. So some of the challenges we face, cancer remarkably changed the vertebra. If you look at the architecture, so the vertebra on the upper left is a normal vertebra, the vertebra on its right is the osteolytic one, there's a mix, there's a lesion, they're very, very characteristics, and the response of that, there's a huge changes in the mechanical and in the strength and stiffness of that vertebra. And current prediction methods do a good job, but not as good as we would like it to do. So we need to develop machine learning method that can start to account for that effect. Not only, but essentially muscles, and we know the sarcopenia in cancer muscles is really predictive of poor outcome in patient, decreased overall survival, shorter disease-free survival, and increased post-operative complications. So can we divide machine learning method to start and interrogate muscle structure and composition and relate it to fracture risk and survival? Because one of those things is if you treat the patient and the patient has no mass, for instance, that treatment will not be successful. So we need to understand how this works. So ultimately, what we want to do is develop DL methods because we're getting excited about the whole thing. So A, to do accurate segmentation, to register and process longitudinal image data, process multimodal information, CT, MR, PET CT, bring them all together and try to get combined information. And from that, really extract multi-parametric features to get a much better prediction of how to assay disease progression in these patients, and then use the DL method to predict failure, treatment efficacy in spinal tissues. So these are some of my collaborators, and thank you very much. And I yield the floor.
Thank you so much, Rudolf. So those 3 mind-blowing clinical applications really give you a sense of how much things have progressed in the last year or so. Thanks greatly to the AWS MONAI, the whole community, 3D Slicer, of course, big part of all these things. So I think there's more to be done. I think all 3 use cases illustrated how much more excitement there is about things that could be discovered clinically. So I'm going to pass it back to Andres to get back to the more sort of technical side. And then also, I think Ching has sent out all the emails for people to start getting their hands on instances going. So we'll sort of migrate into that mode. So Andres, can I pass it to you?
You see my screen, Steve?
Yes, looks good.
Excellent. Excellent. So thank you. So now we are going to discuss different radiology use cases that are already implemented in MONAI Label and the different details with regard to the data set that we use, the number of annotated volumes, number of segments, and architecture. So let's start with the lungs and airways segmentation that Dr. Rudolf mentioned earlier today. So for this specific model, we use the medical cementation decathlon dataset, the task 06 lang task, and then so this dataset doesn't have those annotations, lungs and airways. Dr. Rudolf create the annotations for 87 volumes, and we trained a model in MONAI label model on those annotations. Specifically for this dataset, we use a standard unit, a vanilla unit, and the ROI size of 128 Q. I just want to highlight this in details once, so you remember, you remind that when we play with the AWS plus MONAI label infrastructure later in the presentation. And telling you the number of annotation because it's also you will also experience the performance of that compared to other models that use more annotations. So this is one case, lungs and airway cementation. The other one is the one that Dr. Ron mentioned for spine and vertebral cementation. Specifically for this model, we use the Versi vertebral cementation dataset. A portion of that we didn't train on the whole dataset, and we use only 60 annotated volumes. Specifically for this task, we use the 24 labels, 24 segments, which is the number of vertebrae that most of the humans have. Some of humans have 25 or 26, but in general, 24 is a typical number. In this case, we use an ROI size of 96 EQ, and instead of using a single network, we use a multi-stage approach, which is basically three networks. So the first one is basically localizes the spine, so segment the full spine. The second stage takes as input the first stage and crop around that area, the area around the spine, and then segments the vertebrae. Once the segmentation of the vertebrae are done, we compute the centroids of each vertebra. So the third stage, the vertebra in a more refined way. Okay, so this is a multi-stage approach using the SEC-ResNet architecture, and you can also play with that in the hands-on session that we are going to show later. So another model that is that was trained on MONAI label as well is the whole body CT segmentation model. And for this, we use the total segmentator dataset, which is composed of more than 1,000 images. So we have 1,200 volumes annotated, which is great. And for this, we have 104 segments. I know there are more now, there are more annotation now, but by the time that we train the model, we use the 104. In this case, instead of using multiple networks, we use a single network that predicts the 104 segments. And in this case, we use the SEC-ResNet architecture. You can download the radiology app and the full CT, the whole body CT segmentation model, and run the MONAI label server and play with the dataset if you want to do it locally. In any case, we are going to show that in AWS as well, which is great. What else? You can, so more details about this training is I'm going to discuss it later. Another model that I've trained, and just to make the point of the worthiness of this dataset, the total segmentator dataset, is that you don't need to train a model for 104 segments. So let's say you are focused on specifically on the lung lobes and airways. So you only take those segments. You define again in the configs file. You define the segments that you want to work on, and train the model, the MONAI label model on those segments. Just to make the point, I trained a model only on a third part, on the third of the data set, 400 volumes for 24 segments using an ROI size of 96Q. Again, this is a single stage, single network that predicts 24 segments. And this is the performance. So it works really good. Of course, the number of images is much bigger than previous ones. This is not available in AWS, but you can definitely just, this is just to show the downstream tasks that we can have combining, good data set with MONAI label and AWS resources. Another thing that I want to mention is the whole brain segmentation model that is available in MONAI Zoo. So this model was trained on OASIS and Candy datasets, or specifically on T1 weighted MR images. It works really good on this type of modality. You can start the server, MONAI Label server, pointing to that MONAI bundle and run inference on the T1 weighted images to get the whole brain segmentation. So this is also available. There are more models in the MONAI Zoo, so you can play with that in MONAI Label. Another thing that I wanted to mention, another use case very interesting, is the use of MONAI Label for modeling the brain tumor and brain deformation using MR images. In this case, the Neurosurgical Atlas, which is an organization of neurosurgeons, they use MONAI Label to segment not only the tumor, but also edema and the deformed brain segments. And the idea is essentially to create a virtual twin, digital twin of the patient-specific brain, to then put it into a digital twin of the operating room, so they can navigate the brain to find the best path to remove the tumor, right? So this is another use case of MONAI Label combined with the Omniverse in NVIDIA. Yeah, that you wanted to show that use case as well. So before we go into the use of AWS and MONAI Label, I just want to share some details, or maybe I wanted to, yeah, let's leave it for after the hands-on session. So let me show you the, I can see. Steve, you see the upstream screen, right?
Yeah.
Okay, excellent.
Yes.
So by now you should have received the email with the details to get access to the upstream instance. So the first screen that you will see is the 3D slicer icon plus 3 MONAI Label models that I'm going to show you. So you can either click in any of those. I'm going to start to 3D slicer. And you will see once this started, the 3D slicer on the browser. Okay, starting on the browser. Excellent. So we have the 3D slicer here, and you already have the MONAI Label module installed in this 3D slicer version. You now have the different tabs available in MONAI Label. For that, let's go and start any of these servers. Let's start with the land segmentation model. So you click there, and the MONAI Label servers will start on pointing on that model. So once this starts, I'm going ahead and connect to the server, and you know that you are connected because the next sample button is activated, right? So there are different tabs here in the MONAI Label module. So you see a place to put the IP address to connect to the MONAI Label server. You see the type of application that you're running, in this case, the MONAI Label app, the radiology app. And then you have a tab for active learning. By default, we have a random strategy, which is the vanilla version of an active learning strategy, which is randomly select from an unlabeled image for me to annotate, or for the expert to annotate. Right, so you see the model, we start the segmentation model. You have the segment editor slicer including in this module as well, and you have the automatic segmentation. It's not activated because I don't have any image selected, but let's fetch the next sample. So you see, I will get a CT image, right, to segment. So you now see the automatic segmentation button is activated. I'm going to run automatic inference on this image and show you the results of that. So just to remind you, so this model was trained on 87 annotated volumes, and it was using the vanilla unit, right? So performance is quite good, but it's not as good as we wanted to have. So you see there is some part of the right lung that is segmented as left. Yes, so it's not perfect, and yeah, I just wanted to point out, because for two things. We didn't use enough data sets, and the model was not using the best network for this task, right? Another use case that you can do is, for instance, load an example, say this city chest, and you will see that the performance is definitely not good. So you click to send the image to the server to run inference, and I just want to show you that the results on the test set of the same data set works decent, but you use another data set, the performance is not as good, right? And it's essentially because of that, because we didn't use enough data set to train the model, and also we didn't use the best network. So let's go ahead and try, say, for instance, the whole body city segmentation. So for that, we close that terminal and start the total segmentator model, right? This is essentially the whole body city segmentation model implemented in MONAI Label, and for that we use the total segmentator dataset, right? So connect to the server. In this case, we're going to fetch an example, right? And run inference on this image, for instance. So this model was trained on all the 1,200 volumes, annotated volumes. So the model works much better than the LAN segmentation, even for LANs and the other segments. And also we use a SegResNet, which is a more optimized network to perform that performs better on this sort of task. So the first inference takes around 30 seconds. The second one, because the first one catches the network on the GPU, so the second one takes less than the first one. So you can see the inference is running here. So it's running the inference there. So this is the three transforms that we apply: Gaussian smoothing, and then scale intensity. Run the sliding window infer, right, with a 96 cube patch size, and then the post transforms basically apply the activations, and then the keep largest connected components, and you will get the predictions after that. Yeah. So yeah, you will see this is so it took around 74 seconds to run inference on this image. And you will see the performance of this. You can go here and show the 3D. So this is, again, one network predicting the 104 segments, a MONAI Label model trained on the total segmentator dataset. And I'm going to show you another example. For instance, on this one, which is the city chest, an example. So you see that the performance is much better when you use, of course, more images and a better network, right? So this is to point out that MONAI Label is very flexible. You can train any network as long as you have the data set organized in that way and define the segments. The MONAI Label model will train that and deliver good results. Just 1 second to run inference on that, and let's see, we can track. Yeah, it's running the sliding window infer. We can check the size of the image here. So it's 512. Let me increase this. So 512, 139. That's the size of the image. The model that we're running here is a 1.5 millimeter model. We also trained a 2 millimeter model, and it's also available in the MONAI Label radiology app. So this is running the post transform, and it took around 60 seconds in total to run inference on this. So you see that the segmentation of the LANs is much better when we use better network, more annotated data sets, and and use that for more train the model for more time. So the other bit that I wanted to show you is the so I'm going to close this and show you the vertebra segmentation model, which is a multi-stage model. So I close that and open the vertebra segmentation model. So I reconnect here to the server, and you will see that in the model I have 3 models. So the localization spine, localization vertebra, and the vertebra pipeline. Vertebra pipeline is basically I want to run the 3 stages, right? Localization spine is to see how the model is working on localizing the spine. So you can get intermediate results of that multi-stage approach. So let's say I want to localize the vertebra here. So I want to run inference on this example. So this means I'm using the second stage to segment the vertebra. Let's see, this is running inference here on an image of 512, 512, 240. Again, running the sliding window per 96 cube. It will take 40 seconds, 45 seconds to annotate this.
Does it say device type CPU on the sliding window infer?
It depends. Yeah, you can define. You can use also the CPU, but so you can both use a GPU or CPU, right? In this case, because the GPU that we are using is 16 gigabyte GPU. If that doesn't fit on the GPU, we move to the CPU, right? But it depends. I mean, that's why it's taking more time, right?
Okay.
You can also combine, right? You can also use the depending on so a GPU definitely is needed to run the inference, but then you can run partly of that on the resources that you have, right? Ideally, 16, 12. I mean, depends on the model. This model is 3 stages. Is a bit more. It needs more resources, right? When you have a single network, it uses less. But yeah, that's the flexibility of MONAI Label. You can use it for any model. This is actually taking more time than okay. No. So it took me 136 is more than 2 minutes to run inference on this image, which is quite big actually. Volume 512, 240. It has a good spacing, good resolution. But yeah, anyway, so you can go here and visualize that the cement editor. You visualize the segmentation that you got from the segmentation model for spine. So you see the smoothing of the vertebra, and that's essentially because the model was trained on much better resolution. So I think it's 0.6. The model was trained 0.6 millimeter. But you can train on bigger resolution, right? 0.4, 0.3, or smaller, right? 1.5. But that's the flexibility of MONAI. I wanted to show that. And with that, let me just finish this to say a couple of things about the whole body CT segmentation model, which is one of the using the good resource of the data set, which is 1,000 images. So for those that don't have more than 1 GPU, you can split the data set into several folds. Sorry. And each fold, for instance, I use a single GPU and I split the data set 8 folds. Each fold are 150 volumes, and train a MONAI Label model on the first fold for 300 epochs. and then fine tune that model on the other folds. So that in that case, you can easily get a model train on MONAI label model train on this data set. This is for 104 segments, right? You can define the number of segments that you want. Say you want to focus on only vertebra or only the spine. You take only the labels for the spine. In this case, I trained two models again, 1.5 and 2 millimeters. But you can increase the resolution. For that, you will need more resources, bigger GPU. But you can do that definitely in MONAI label without any major changes. Just in the config files, define the spacing. Specifically for this model, we got the 85% dice score on 10% of the data set. Again, it was using a single network, the SecResNet, for 104 segments. We didn't use the new labels available in the total cementator data set, such as skin, coronary arteries, and the others. We used the original 104 one, the first ones. And just to repeat, this is the script that I used to merge the labels and organize the data set, so MONAI label can use it to train and do other tasks. Cementing instead of 104, you segment only 5 or 2 or 3 or 24, which is the number of vertebrae. Yeah, there is a lot of flexibility. It's a platform that you can use for anything really. Single stage, multiple stage, and that's it. I think with that I'll conclude, so we can go and play with the basically I did that already. I have a bunch of questions that we can frequently ask questions, but if there is any question, I think this is a good time. What do you think, Steve?
Yeah, I think this is great, and I really appreciate the context here. We have this really incredible clinical use cases, and then like the step-by-step instructions to how to recreate. And I know it's a little bit of a leap to go from one to the other for everybody, but hopefully the hands-on session. I know Ching has helped a lot of people get their workstations set up. If people still have trouble, they can go to Discord, but I thought maybe, I don't know if someone has theirs set up and wants to ask questions about making sure they understand how to access all the things that Andres was showing. Is there anybody here who has questions? I've seen some in the chat. Maybe want to throw those out. For example, Hans Meine, I'm going to call on you because I know you were working on getting yours set up. Are you now able to run the MONAI label if you are here? No, Hans? No, he may be still working on his instance.
No, I was called away from the computer.
Okay.
Yeah, I managed to do to run the application. I don't have a question at the moment, but I remember that I posted one in the chat.
Yeah, would you mind being like a little bit of a guinea pig and just show everybody how to recreate what Andres was doing? Because that may help people, because I know there's there's really only a few steps involved, but
okay, yeah, I can try. So I share my screen.
Yeah, see it.
Should I start from scratch? Because one thing that took me a little time is to understand this upstream interface. Yeah. So at the top left, you have this small icon, and there you have the same choice of applications as in the front screen. And I started 3D Slicer and the Total Segmentator MONAI Label server. Mm-hmm. And then in Slicer, so MONAI Label server means that you get, now I don't know why I can't.
I think the button right next to the on the toolbar, there's the little icon where you launch the app. Right next to that, there's sort of a task switcher. That one, yeah.
Oh yeah.
That one lets you
exactly.
see.
So before I just moved the window and it worked. Now it doesn't work for some reason. So the MONAI Label server gives me this terminal window, that we saw in the demo. And then switching back to Slicer, I had to press this reload button to connect to the server. So the app name appeared, and then I think I pressed next sample, which we also saw in the demo to, maybe I can press that again. But somehow Slicer at the moment doesn't react to most of my interaction. So when I move my cursor, I can see at the bottom the data probe is doing something, which it maybe shouldn't do at the left, right?
Yeah, that's interesting. Well, one thing you can do is maybe just try restarting it. It could have been, it looks like it may have gotten into a...
Yeah, somehow I don't know if I can even close it, because the close button also doesn't work.
Could you try just refresh the page? If you move your cursor to the URL tab, just hit enter.
Yeah, there's actually I can't see there. Probably you can see better than me because there's an overlay from Zoom.
Yes.
Yeah, or just click the refresh button on the top left in your browser toolbar.
I have tried so.
Oh, reload.
There we go.
Okay, so
work now. It still looks like it.
They don't. Maybe someone else should. Oh no, this works, but the slicer buttons don't work. And also, I didn't purposely change the view here. Is it possible that I have started multiple slicers?
That could be.
Would that happen?
I think you double click. I think you double clicked on the view. If you double click the view, is it restored? If you double click again on the slice view, yeah.
Oh yeah. So I double clicked somewhere here, and yeah. Right.
I think
so it always thinks that it's in this view. Yeah.
I think it just doesn't fetch the sample. I don't know if there are samples set for this data set, but it seems that the next sample that doesn't seem to work. But otherwise,
I'm afraid.
It looks like the mouse is somehow off.
Yeah, the mouse is off somehow.
Yeah. So Ching, is it easy enough to reboot the machine from this interface for?
Yeah, yeah. The easiest thing.
Close?
No, the easiest thing to do. I think the easiest thing to do is just log out. If you just go to your top right, and then just log out, and then log back in. And when you do that, you will get the new instance assigned to you. So, and you can try doing the same thing again.
Right. Should I already start one of these? Maybe try this one.
Sure.
This time.
It doesn't matter which one you start first. Yeah, when this is loading, and then you can set up. You can launch 3D Slicer next. All right.
Thank you for being a good sport, Hans. We're sorry to put you on the spot with this.
Yeah, no, I'm in home office and I was just called by my kids, so don't know if this is the fastest way to get there, but it works.
Yep, this looks good.
And I connect to the server, and then pressing next sample gives me a random image. Oh, this one looks interesting. And then I can now try to segment the vertebra by
just clicking there.
Going here, right? So I have even a choice of 3 algorithms: localization spine, localization vertebra, and vertebra pipeline.
Yeah, can you remind? I don't remember the right method here. What's the Andres? Can you remind us the sequence?
Yes, you can use. So actually the vertebra pipeline is the 3 stages, right? The other
all 3
the
stages.
first one, yeah. The first one is.
Let's go for that, right?
Yeah.
I want to see everything, so that's why I go for that one.
Now, this is also a Windows instance, so if we wanted to, we could probably bring up the task manager as well and look at the GPU and CPU usage, but that may be an advanced topic. But sometimes if you're curious what goes on during these, but I don't know how to do it on the PC, on the app streaming for sure.
I can show you how to do that.
Okay.
So
Oh,
you can open a new tab. If you click on the file in the terminal window.
Here.
Here, yeah.
Okay, yeah.
It's a new tab. And if you want to monitor the CPU memory usage, just type htop, HTOP.
Oh, okay. So this is actually a Linux machine.
This is a Linux machine, so we got
okay.
16 virtual CPUs. Yeah, you can do that to monitor the graphics card usage as well.
Yeah. Yes, cool.
Nice.
Maybe.
Yeah, it's funny. We always used Windows machines for our app streaming before, and I didn't even notice the difference.
So I think it's running already the last stage.
Without GPU, right?
You can scroll up and see the different stages. So those are the logs.
And the first time you are running the inferencing, it's gonna be a little bit slower because
oh yes,
there's the time taken to cache the model, right, Andres?
Yes. Usually the second time you perform inference, the second volume, it takes 20 seconds less than the first. So it takes apparently 11 vertebrae.
Okay, I see something. Now comes the moment where you tell me that I'm not good at Slicer. Because,
no, this looks great. You've already segmented the spine when you.
Yeah, last time I had problems going here into the segment editor because the problem was that my mouse really didn't reach the buttons, but apparently this works this time.
Yeah. Now, is this a spine with a fracture, or is this just a?
No, I think this is a mis-cementation. Yeah.
Okay.
So this is this is a nice case I wanted to show us. What we use only 60 annotations to train the model, and the reason for that is basically I just wanted to train the model and for you to see how that works and how it works for the total cementator, for instance, when you use the 1,000 volumes, right? So this means that this network needs more training and more annotation to get better. The other, there was another question regarding the. I think you asked.
Yes, I asked that. So you already answered my question. Why you only chose a subset? Because I thought, okay, if you download the full data set, the training will not run longer if you have the same stop criterion. It will just see different cases. So I thought that would be a good idea too.
Yeah.
I think the way MONAI label set up, it usually is set a fixed number of epochs and iterations, not a stop criterion. So maybe.
So if you go, for instance, yeah, because that's the very, very good question I haven't gone through. If you go, for instance, to the what is it, the active learning. I don't know why it doesn't show the.
I have to enable this developer interface, maybe.
No, if you scroll up in the MONAI label plugin, there is segment editor. Why I don't see the?
Oh, he's not in developer mode.
Yeah, I think that's the reason.
How do I enable that? By here?
Application settings, yes. MONAI label, the second, yeah, that one. And then developer mode, yes.
Anything else I should change?
I think you need to. do you know how to reload the plugin, Steve? Also
sorry,
activate the developer mode in Slicer. So you go to the what is a developer in
in
the
developer.
List of, yes.
Yeah, the tab called developer. There you go, and then enable developer.
Yeah.
Yeah.
Okay. It will ask you to restart Slicer. Yes.
Okay, I remember that faintly from last year. I think I had the same learning back then. But for some people, it was already in developer mode, I remember.
Yeah.
I think it depended on the region or so.
Mm.
Would it make sense to move those settings maybe in a advanced section or something, but not require developer mode? Because I see on these demos, it always comes up that, yeah, you need to enable a developer mode and so on. It might be just an advanced settings section to hide
see
it.
there
But
now you. Oh, yeah. I'm sorry. Now you have the options, but I agree.
Yeah. Good point. Yes. Something like advanced settings. We open an issue. I mean, Sachi open an issue at the other MONAI Label developer to reduce also the installation process of MONAI Label or the start server of MONAI Label on Windows and Linux. So the idea is to facilitate that as well. Yeah. So there you see in options you see infer. So you open options that there is infer and train, and by default there is the train is only 50 epochs. So you can update that. You can add more epochs. You can change the type of data loader. You need to minimize the other tabs to see full.
Too many user interface elements here. Okay, yes.
So you see the number of epochs. You see the percentage that is going to use for validation. Whether you are going to use multi-GPU if you have more than one GPU. And also we use MLflow to track the training and validation. So that's the bit. I agree. Something like advanced settings will be more easy. Yeah, we always try to reduce the number of buttons that people will use. But that's a really good point. Anyway, so this is the bit. There was another question regarding the functionality of next sample, something like going to the list of all the images. That's definitely possible. You can modify that. Is not hard coded.
It's also possible easily to just drag and drop new studies, new files into Slicer and then run on those in your however you like.
Yes. That's also very. Let me see if there is another question here. Yeah, can I do presentation on my laptop? Sorry.
Shall I stop sharing now?
This has been great. Yeah, no, thank you for doing this.
Thank you.
I know we're coming close to, we got about 5 minutes left before people might need to go to that MONAI boot camp. I know Michael Zephyr might have already left for that. But yeah, if you want to finish up more questions or people want to post real quick ones before we all fade away. There was that question about what happens if the people have extra vertebrae. How do they get labeled?
No, I'm afraid not. No, because the model was trained on 24, right? That's the issue. You will need to retrain the model for the model to detect the other, right? So if you train a model that detects liver, say you have a spleen, it will not recognize the spleen, right? That's similar.
Yeah. But it has been really robust, and that was one of the earlier questions about what happens when you have variety of different data types, and it has been very robust at, like, for example, if the scan only goes from the chest up, it doesn't include a liver, right? So it's pretty robust in terms of recognizing what things are what.
Yeah.
I have a quick question if I could post.
Sure.
First of all, I'd like to say hello to the community. I'm probably typical of a clinician with very little computer science background who was drawn into this. And actually, it was Andres's video, the MONAI Quick Start, that introduced me to all of this. And I think for people like myself, if we could dumb down the instructions about what criteria are needed, it might help. For example, like I started with a very sort of modest workstation and quickly ran into issues with not being able to run some of these models that required a high GPU requirement. And I think that this AWS collaboration is going to be fantastic if we could point people in that direction. The threshold to being able to do their own work, I think, is going to be lowered significantly. But my only question was, if we're running these, I guess, samples on the AWS platform, how do we point our own data to use on the AWS platform? And also, is it reliable to assume that the patient content, because we're going to be using clinical X-rays, not data sets that have already been stripped. Is it reliable, and is it going to sort of pass the sort of these ethics questions about how robust the personal information stripping is going to be? Thank you.
Andres, do you want to take that on?
Yeah, I think it's more on the if Shin can comment on the security bit, on how you can upload the data set on AWS and data anonymization, if I understood correctly, and how that can be basically security.
Yeah, or I can tell you from my experience that so I do a lot of work with Mass General Brigham at in different hospitals, and Ron Alkalay is on the call he presented earlier for Beth Israel Deaconess. And the way it works for most institutions that I've worked with is that there first is a discussion with the institutional sort of research management about like what will and won't be sort of acceptable projects to do with patient identifiable information. And I think at least for most institutions, there's a institutional agreement between AWS and the institution about like how they're going to manage these things. Once that's done, a wide variety of de-identification techniques are usually used to make sure that any data that's uploaded is as secure as possible. That there's no reason to expose data that otherwise isn't needed for the research involved. All those things being said, it is practical in my experience for an institution to make use of either AWS or other cloud services as part of the research activities. But obviously, institutional review boards and other things need to be involved to make sure that you're not doing something, accidentally that's more risky than it needs to be. I'm guessing Alex might actually be the right one to grab into this topic.
Yeah, so thanks, Steve, for highlighting some points, and thanks for the question, Samuel. So in short, also in the interest of time, because we already are at the hour, usually when you use AWS, you are the owner of your data, right? So AWS is not touching it, and security is our job zero here at AWS. So we will help you to actually set up your AWS account in the best possible manner, but it will be you managing your own data, actually also making sure that only authorized people, systems can access it with the right toolings on the security side and also on the authorization side. Again, it will be maintained by your organization, and also for instance, when you move some of your PACS systems, either research PACS or clinical PACS to the AWS cloud, they will run in your AWS account, which you manage.
Okay.
Yep.
But just the robustness of the stripping of the personal data that the MONAI label, I guess, that does do the anonymization automatically, does it not? No,
okay. I think that's the point, is that
because when I tried to add my own films to one of the data sets, it says that this is happening. There is a little blurb that says that the data is being anonymized and it's being sent to the server, but
that does happen. If you're running a server, then only the minimal amount of information needed to run the inference is run. If the server, for example, is whether it's on AWS or local. So you do need to be aware that if you're sending patient data to a server running on AWS, you should be doing that in accordance with your local.
So that's right. So
Yeah.
basically prepare all the data and then send it. Yeah. Okay.
Yeah.
Super. Thank you so much.
Okay. I see there's some more questions. I know some of us have to leave for other commitments at 11. So if people want to stay on, I think maybe Mauro has another question, but otherwise I think we should probably wrap up the recording. And thank you everybody for coming. I know Michael probably has already left, so I don't know who can end the recording.
Yeah, I can end the recording.
Okay.
Thank you everyone for coming, and I hope you enjoy the workshop.
Yeah, thank you to Rudolf and Ron and to Dr. Butcher and of course to Andres and everybody who really put in a lot of effort to make this happen, Jing and gang especially. Thank you.
Thank you everyone. Thank you, Steve.
Thank you.
Thank you.
Thanks, Steve. Bye.